In this video, we're going to look at a few more theoretical examples of infinite series. So the first question is, find the value of c such that the summation n goes from 0 to infinity e to the power of nc. This sum is equal to 20. And so the first thing we want to do is expand this series term by term. So we have summation n equals 0 to infinity e to the power of nc. This is equal to, plug n equals 0, we get e to 0, that gives us 1, plus n equals 1, we get e to the c, plus n equals 2, we get e to the 2c, plug n equals 3, we get e to the 3c, and the general term would be e to the nc, which we can write as e to the c to the power of n, and this is an infinite series, so dot dot dot, and this whole sum is equal to 20. Our job is to find the value of c that makes this series converge and have a sum of 20. Now clearly this is a geometric series with a first term, which is 1, geometric series, where a is equal to 1, and the common ratio is e to the c. Why do we know that? Is because every term, if you multiply the first term by e to the c, we get the next term. Multiply the second term, which is e to the c, multiply by e to the c, we get e to the 2c. So the ratio of successive terms is e to the c. That's how we know it's a geometric series. Now, for this infinite geometric series to converge to a finite sum, we need absolute value of r to be less than 1. That means absolute value of e to the c must be less than 1. Now, exponential functions are always positive, so we don't need the absolute value. That means e to the c is less than 1. Log both sides, we get ln of e to the c is less than log of 1. Log cancels e, and we get c is less than log of 1 is 0. That means c has to be less than 0. It has to be a negative number for this geometric series to converge and have a sum of 20. But we need to find the exact value of c. So what we have is summation n goes from 0 to infinity e to the nc is equal to 20. Let's rewrite this geometric series as n equals 0 to infinity e to the c to the power of n is equal to 20. The reason we rewrite it in this form is because we want to show the common ratio, which is e to the c, r equals e to the c. So we have a is equal to 1, that's the first term, and r is equal to e to the c. Now we have the summation of the sum of a geometric series is equal to a over 1 minus r. So the sum is given as 20 is equal to, the first term is 1 divided by 1 minus the common ratio, which is e to the c. Now let's cross multiply and solve for c. So let's write the left hand side as 20 divided by 1. Cross multiply and we get 20 minus 20 e to the c is equal to 1. Now we get 20 e to the c is equal to 19. Divide both sides by 20 and we get e to the c is equal to 19 divided by 20. Now to solve for c, we're going to log both sides, so we get log of e to the c is equal to log of the right-hand side, log of 19 divided by 20. Log cancels e, and we can solve for c. c is equal to log of 19 divided by 20. Now, if c is equal to log of 19 divided by 20, this geometric series will converge. This infinite geometric series will converge and have a sum of 20. So summation e to the nc, n equals 0 to infinity, we can rewrite this by plugging in the value of c. So summation n goes from 0 to infinity e to the n log of 19 divided by 20. This infinite geometric series converges and has a sum of 20. All right, let's look at another example. Here we have the nth partial sum of a series, summation an, is given as Sn is equal to 2n minus 1 divided by 2n plus 1. Our job is to find the nth term, an, And we also want to find summation an, the sum of this series. All right. For this type of question, we're given the partial sum Sn, and we have to work backwards to recover the general term an. So the general term an is simply the subtraction of Sn minus Sn minus 1. This gives us the general term an. So Sn minus Sn minus 1, we have the nth partial sum. It's given as 2n minus 1 divided by 2n plus 1 minus, now Sn minus 1, plug in n minus 1, so we get 2 times n minus 1 minus 1 divided by 2 times n minus 1 plus 1. If we simplify this, we get 2n minus 1 divided by 2n plus 1 minus 2n minus 3 divided by 2n minus 1. Now an is equal to, let's add these two fractions. In this case, I guess I should say let's subtract these two fractions. We get 2n plus 1 times 2n minus 1 is a common denominator. And 2n plus 1 goes into this common denominator 2n minus 1 times. So we get 2n minus 1 times 2n minus 1 minus, and 2n minus 1 goes into the common denominator 2n plus 1 times. So we get 2n minus 3 times 2n plus 1. Simplifying the numerator, we're going to get 2n times 2n. That gives us 4n squared. And we get minus 2n minus 2n, we get minus 4n plus 1. Subtract. 2n times 2n gives us 4n squared. 2n times 1, that's 2n minus 6n is negative 4n minus 3. Minus 4n minus 3. All divided by 2n plus 1 times 2n minus 1. Let's simplify this so we can have the general term an. All right, so we have Sn minus Sn minus 1 is equal to, if we simplify this, we're going to get, we have 4n squared minus 4n plus 1 minus, distribute the minus sign, minus 4n squared plus 4n plus 3, all divided by the denominator, which is 2n plus 1 times 2n minus 1. 4n squared cancels with 4n squared, 4n cancels with minus 4n, and in the numerator, we just get 3 plus 1, that's 4, divided by, and in the denominator, if we simplify this, we have 2n plus 1 times 2n minus 1, so we get 4n squared minus 1. This gives us the general term an. So now we need to find the sum of this series. Summation n goes from 1 to infinity of an. This is the sum of the series that we need to find. So we basically take the limit of the nth partial sum, and this will be easy because we're given the nth partial sum, Sn. And take the limit as n goes to infinity, that gives us the sum of this series. So let's take the limit as n goes to infinity, and we're given Sn to be equal to 2n minus 1 divided by 2n plus 1, and we solve for the general term an is equal to 4 divided by 4n squared minus 1. So let's take the limit of Sn as n goes to infinity. So that's going to be limit as n goes to infinity, 2n minus 1 divided by 2n plus 1. Dividing by the highest power, divide by n, take the limit, and we get 1. This is equal to s. So the limit of Sn as n goes to infinity is equal to limit as n goes to infinity, and Sn is equal to 2n minus 1 divided by 2n plus 1. Divide by the highest power, take the limit, and the answer is 1. This is the limit of the sum. So we can write summation an, n equals 1 to infinity, summation an, and we solve for the nth term. That summation n goes from 1. This infinite series has the sum of 1. So an is 4 divided by 4n squared minus 1, and this infinite series has a sum of 1. It converges to 1. When we say a series converges, it always has a finite sum. In this case, the sum is 1. All right, let's look at another example. Here we have show that for all real values of x, sine x minus 1/3 minus 1/3 sine squared x plus 1 over 9 sine cubed x minus 1 over 27 sine to the 4th x plus dot dot dot. The total sum of this series is 3 sine x divided by 3 plus sine x for all values of x. Now clearly this is an expanded form of a geometric series. With the first term is a is equal to sine x, and the common ratio r is equal to, what is the common ratio? Well, you will notice, if you take the first term, which is sine x, and multiply it by minus sine x over 3, you get the next term, which is minus sine squared x over 3. So we know the ratio of successive terms is always going to be minus sine x over 3. Any term, if you multiply it by minus sine x over 3, you'll get the next term. So common ratio r is equal to minus sine x divided by 3. Now, for this geometric series to have a finite sum s, we need absolute value of r, absolute value of the common ratio, to be less than 1. That means absolute value of minus sine x divided by 3 should be less than 1. So that means absolute value, simplifying, we get absolute value of sine x divided by 3 should be less than 1. Now, we know that absolute value of sine x is always less than or equal to 1 for all values of x. Sine is always less than 1 because sine is a ratio of its opposite over hypotenuse. Its magnitude is always less than 1. That means that absolute value of sine x divided by 3 is less than or equal to 1/3 for all values of x, which is of course less than 1. That means the common ratio, which is equal to absolute value of minus sine x divided by 3, this common ratio is less than 1 for all values of x, for all x. So what we have is absolute value of r is equal to absolute value of minus sine x divided by 3 is less than 1, and the infinite geometric series converges, and the infinite geometric series converges. It converges to a finite sum, converges to s, where s is equal to a divided by 1 minus r. A is the first term, a is equal to sine x, and the common ratio r is equal to minus sine x divided by 3. So s is equal to a divided by 1 minus r, a is equal to sine x, divided by 1 minus r, which is minus sine x, divided by 3. Multiply top and bottom by 3 to get rid of the fraction, so we get 3 sine x divided by 3 plus sine x. This is the sum of this infinite geometric series, and this infinite geometric series converges to the sum for all values of x. So we have sine x. Let's write the expanded form of this geometric series. Sine x minus 1/3 sine squared x plus 1 over 9 sine cubed x minus 1 over 27 sine to the 4th x, and dot dot dot. This is an infinite geometric series. This is equal to, the total sum is equal to 3 sine x. It converges to this sum divided by 3 plus sine x. Now we should always be able to write the compact summation form for a geometric series because we have summation a r to the n minus 1. This describes the pattern of a geometric series. So we have summation n equals 1 to infinity, a is equal to sine x, r is equal to minus sine x divided by 3 to the power of n minus 1. This is the compact form of this geometric series, and this infinite geometric series converges to this sum, 3 sine x divided by 3 plus sine x for all values of x. Converges for all values of x. All right, thanks.